Good evening. I'm Spot On Weather meteorologist Matthew Euler. Tonight we're going to take a look at air masses. Very interesting topic. Obviously, air masses play a large role in what kind of weather we get, and they do vary by season from summer to winter time. This map here on the title slide just shows you a lot of different symbols representing a lot of different air masses. So we'll go ahead and get right into the training right now. We're going to start off, and really what it comes down to, you see the bottom right graphic there, it says polar versus tropical. Um, the equatorial regions are heated much more greatly as compared to the polar regions, and as a result, equilibrium. Nature tries to create equilibrium in the form of storms, mid-latitude cyclones, typically, especially in the wintertime, and even in the late fall. And in the summertime, nature creates hurricanes to try to redistribute the hotter air, the excessive heat of the equator towards the colder polar regions. Air always flows from hotter towards colder. So these air masses make up a lot of that mixing that's necessary to strengthen storms and to really redistribute that excess heat from the equator towards the poles and then bring colder air from the poles further south in latitude. All right, so the definition of an air mass. What is an air mass exactly? It is a widespread body of air with similar temperature and moisture characteristics in any horizontal direction at any selected altitude. It's most relevant in the lower troposphere where we live. Now, the birth of an air mass. How are air masses born? Well, they're born over what's known as an air mass source region, and this is a large area of generally level terrain. It's generally fairly flat in an air mass source region. You really don't have a lot of mountains because we don't want a lot of mixing. We don't want a lot of rising vertical air motion, and you get a lot of that in the vicinity of mountain ranges. So you want a generally large area that's fairly flat, an area with light winds and uniform temperature and moisture characteristics, usually located outside of the middle latitudes. Why do air masses not really form very well in the mid latitudes? It's because there's always so much mixing of airs. There's usually too much wind. So an air mass really can't accumulate over the flat source region. A lot of mixing in the mid latitudes with cyclones. Now, source regions, they may undergo large seasonal variations in size due to changes in that shortwave solar, the sun, and long wave earth radiational budgets. Some source regions are more active in certain seasons. So some source regions are actually stronger in certain seasons. For example, when we talk about the continent, we talk about Siberia. That source region for very extremely cold continental Arctic air, that is more active in the wintertime when we have a snowpack where the day length is much less, the amount of daylight hours is much less, and then you don't really have much as far as solar radiation is much less. The sun is much lower in the sky at higher latitudes over Siberia. So in this case, that source region over Siberia would be much more active in the wintertime, the colder time of year, as compared to the warmer time of year. And that's just one example. This is a map that just kind of gives you multiple areas of source regions around the world. And one thing that's different between the northern and southern hemisphere is the northern hemisphere is composed of 60% landmass and 40% water, whereas the southern hemisphere is the opposite. The southern hemisphere only has 40% landmass and 60% water. So there's much more water south of the equator in the southern hemisphere as compared to the northern hemisphere. So one air mass, for example, you'll notice is not in the southern hemisphere. That would be continental polar, and that's abbreviated by that C and the capital P. All right, and that's because land heats and cools 5 times quicker than water surfaces, and with so much water and ocean in the southern hemisphere, they just don't get a lot of buildup of cold, dry air, which is continental polar air. So that's just one example. But this just gives you a great look at the various source regions around the world. If you see an M, the letter M in front of something, that means maritime. And we're going to get into that here in a minute. Maritime being of water origin, and then P being polar and T being tropical. So we'll get right into that here with further explanation as we go along in the training. All right, so classification of air masses. What's the geographical source region indicator? So now we're going to break down the actual letters and what they mean. When I show you these letters, these two letters for identifying every air mass, I'm going to tell you exactly, we're going to break that down now. So the first letter, actually the second letter, my bad. The second letter in these air mass identifiers refers to the geographical area, the air mass and its acquired temperature properties. Okay, so if you see the letter A, that implies very cold air, and that letter A stands for Arctic or Antarctic. The letter P implies cold to cool air, and it really depends on whether you're talking about polar air over water or land. Over land, that polar air is going to be much colder and drier as compared to over water. Tropical, that's represented by the letter T, that implies very warm to hot air. Okay. Now the moisture indicator is the first letter of the air mass, and this is the area where air mass acquires its moisture properties. M, I kind of already hinted at this, but M really stands for maritime or of oceanic origin. Somewhere that air mass is forming is over water. It implies moist. Continental is abbreviated by the letter C, the lowercase letter C. This implies dry air, and it's of continental origin, or it generally forms over land and away from a water source. Now, stability is normally not a good indicator of air mass type, because stability within the same air mass may change or fluctuate from one location to another. Okay, so we'll get into the aspects of stability and air masses a little bit later on. So this is an example of stability and how things change. I did talk about this in a previous training about cow, the letter C-O-W, and W-O-C is walk. Okay, so with the surface below the air mass, now that's very critical as far as changing the properties of the air mass, and also with the stability aspect of the air mass. So for example, if I have a surface that is colder than the overlying air mass, that may make the air mass more stable. In that case, you're going to have a warm over cold situation, and anytime you have a warmer layer higher above a colder layer, a warmer over colder layer, that leads to more stable atmospheric conditions. That's the representation there on the right, the WOC, warm over cold, stable. A surface warmer than the overlying air mass, however, may make the air mass unstable. In this case, we talk about the cow, cold over warm. And, we always say don't tip the cow, right? Because that's an unstable situation. So cold over warm. So you have to look at this. Where's your warm layer? Where's your cold layer as these air masses move out from their source regions? That's going to impact the stability and ultimately the weather at a location. Now, air masses can definitely change over time. An air mass that is changing properties, that's an air mass modification, and they will change with time. As the air mass moves out of the source region, it moves over a surface of different moisture and temperature characteristics, and it begins to acquire these traits. The air mass begins to modify. So for example, let's say we have a continental polar air mass in the wintertime that starts off over Canada. And as it moves south, it's going to slowly warm because as you move further south in latitude, the surface below the air mass is going to be milder as you get further south. So a good example is, with a continental polar air mass in Canada in the winter, you may have a temperature below zero initially over the air mass source region in Canada. By the time the air mass moves out of the source region and gets down to the Gulf of Mexico, to the Gulf Coast states, Mississippi, Alabama, Georgia, that air mass may have warmed 40 degrees Fahrenheit. So yes, that does make a difference. As air mass moves, they do change over time. And that's an example of a thermal change. Air masses also undergo moisture changes. So for example, if I have an air mass, we'll use continental polar again, moving from the eastern United States, from the colder land, once it moves out over the warmer waters, especially over the western Atlantic with the Gulf Stream, that air mass is going to change significantly as moisture properties. It will start off dry, but by the time the air mass is through its final modification, it's going to be very moist. Additionally, air mass can be forced to rise and or sink due to terrain changes or mountain ranges. For example, as maritime polar air comes in off the Pacific Northwest, it is going to run into, I'll use the Cascade Mountains up in the Pacific Northwest as an example. As that air mass is forced against the mountain range there, it's a north-south oriented range, that air mass is going to be much different on the leeward side as compared to the windward side due to rising air motion, all the moisture falling on the windward side, and then sinking warming air motion on the leeward side. So yes, mountain ranges play a big role too in air mass modifications. Now let's get into the different types of air mass source regions. Where do these air masses form? Right, we're going to start with continental polar, and it's abbreviated C and P, continental polar. Source regions for this air mass are Canada, Alaska, Siberia, and sometimes even Europe. They're also found over frozen oceans, such as the Arctic Ocean, where there's very limited moisture. When a water body at higher latitudes freezes, there's just simply no moisture that's going to be evaporated from the surface because you have a solid sheet of ice over it. So you just don't have that moisture being transferred into the air mass. And so that air mass, that'd be an example of continental polar air mass right there, forming over ice. Right. So what are continental polar air mass, what type of pressure systems are associated with continental polar air masses? Usually it's associated with a polar high pressure system. These are stronger in wintertime when the landmass is much colder at higher latitudes due to weaker solar radiation, lower sun angles, as well as shorter amount of daylight hours. So in wintertime, these polar high pressure systems can bring some very cold air down into the lower 48. So continental polar is associated with polar highs, generally over land or over frozen oceans is where they form. They intensify in winter because the air mass, the land mass is much colder. And they weaken in the summertime because in the summertime you don't have a very strong temperature gradient between the across the latitude. So the polar highs in the summertime, that continental polar air mass might bring some much needed relief from humidity. Maybe it just brings the humidity down and lowers it. But there really won't be a noticeable temperature change in the summer as compared to winter continental polar air mass and the polar high pressure systems. The general characteristics with the continental polar air mass is it's cold and dry. It's very stable in its source region as well. So winter characteristics, it's dry, it's cold. This dry air is the kind of dry air that really makes it very dry indoors if you don't have humidifiers. Whenever you touch something and you feel that shock, if you touch something or you get that real itchy skin in the wintertime, this is because of the continental polar air masses. They're extremely dry. They're very cold, below freezing, and many times they're going to be less than 0 degrees Fahrenheit in the source region, especially in the wintertime. You have strong surface-based inversions that often are observed in source regions because it's very stable. When you have very cold air, it's dense and it tends to want to be closest to the ground. So sometimes what happens is you get this inversion where the temperature actually is warmer above the ground, and that's known as an inversion. And clear skies generally predominate with this type of air mass with continental polar. In summertime, as I mentioned, it may have relatively low temperatures in the source region, but generally those temperatures up in the far northern Canadian area, those land masses, generally the air mass is above 32 Fahrenheit in source region, except over ice and snow where it's going to be below freezing. Relatively low dew points, which give dry character to the air mass. These are the kind of air masses that can really dry the air out. In summertime, this gives us a nice break, a very nice, much needed relief from the humidity of summer. Continental Arctic air, on the other hand, this is very, very cold air. It's abbreviated by the letter Ca. Source regions are Greenland, northern parts of Siberia, Alaska and Canada in wintertime, and Antarctica. In the late fall is when the continental Arctic air forms, late fall, winter, and early spring only. So this is a seasonal air mass. It doesn't show up in the summer. Characteristics of continental Arctic, it's an extreme form of a CP, or continental polar air mass. And it's normally very shallow, extremely cold, extremely dry, generally extremely stable in its source region. Just think about this. Continental Arctic air is even colder than continental polar. And this air mass is very shallow because the air is so cold, it's so dense. That coldest air really hugs closest to the ground, to the Earth's surface. Air mass source region and associated pressure systems. How is continental Arctic air formed? It's produced by extreme radiational cooling over continental snowpacks during wintertime, and long periods of clear skies help promote its development. On clear nights with a snowpack, you generally have very effective radiational cooling. So therefore, temperatures can get extremely cold over the source region with this type of air mass. And this air mass is associated with extremely cold Canadian high and Siberian high events. So whenever you hear the Arctic Express, the expressions in the wintertime, here comes the Arctic Express into the eastern U.S. or central U.S. or the northern plains. This is exactly the type of air mass we're talking about. We're talking about the record-breaking cold air masses that you see, sometimes associated with the polar vortex. That's that continental Arctic air mass. Extremely cold. Record-breaking, below zero wind chills, below zero temperatures. Yes, that is continental Arctic. Now, the eastern sides of these continental Arctic high-pressure systems as they come down from the source region often reside beneath extremely low heights. You get low upper-level heights on the western side of deep troughs, and these low heights within the upper-level trough are indicative of very cold air in the lower troposphere. And when these low heights overlay continental Arctic air near the surface, you get extremely low thickness values. If you look at something called the hypsometric equation, it basically states that thickness and temperature are directly proportional to each other. So what does that mean? That means the lower the temperature, the lower the thickness of the atmosphere. The center of a continental Arctic high-pressure system in polar regions often does not reside under the lowest thickness values, however. Yet the coldest surface temperatures are generally found near the high center, where you have the radiational cooling is maximized. Right at the center of these Arctic high-pressure systems, you have extremely light to calm winds and clear skies, which aid in very effective radiational cooling, especially in the nighttime hours. And so you get your coldest surface temperatures found directly beneath these Arctic high-pressure centers. Now, there could be a sharp inversion, and most likely will be. Again, inversions referring to temperatures actually warming with height. So sometimes you get the extremely cold, dense, heavy Arctic air closest to the ground, and that's associated with you get this extreme radiational cooling of the surface during the polar night, and then also compressional warming aloft due to sinking air or subsidence. So sometimes you get the high pressure and it's so strong that air sinks from aloft. As air sinks aloft, it warms, and sometimes what you get is an inversion where the temperature is warmer above the ground again. Now let's move into another type of air mass, and this is the maritime tropical air mass, abbreviated with the initials M, lowercase m, capital T. The source regions for maritime tropical are tropical and subtropical oceans. And the oceanic subtropical high pressure systems, these reside within the MT source region. For example, the Bermuda, sometimes we call it the Bermuda Azores High in the Atlantic. Trade winds are dominated by MT air masses. Okay. Here's an example of a Lake Charles, Louisiana. This is a skew T. This is a sounding, and what we're showing you on the right, that black solid line, is the temperature, and the line on the left, the dashed black line, is the dew point. This is a typical maritime tropical air mass sounding. This sounding was taken in June of 1968, late June, and this is at Lake Charles, Louisiana. And this would be, this would be in the evening hours. Generally, you have a very moist air mass at the surface. You have dew points. Dew point temperatures at this point in time are about 77 degrees Fahrenheit, and the surface temperature at this point in time is about 85, 86 degrees. So maritime tropical air masses are the air masses that make us feel so sticky and make you sweat when you go outside. When it's really humid and muggy in the summer and you try to get some yard work done, and next thing you know you're just drenched and you're hardly doing anything at all, you can blame that on the maritime tropical air masses, because that's what's happening. The lower atmosphere is so loaded with moisture. As you notice, though, as you go aloft, these lines, the solid black line on the right and the dashed black line on the left, they spread apart further, and that indicates drier air aloft. But closer to the surface, it's extremely muggy and it's extremely, just real humid. What are the general characteristics of maritime tropical air masses? They're very warm and moist in the low levels. Again, blame these air masses on those miserable, muggy summer days across the eastern United States when you get more of a southerly wind component around those subtropical high pressure systems. Just makes it nasty. You get sinking air subsidence, and you get what's known as a subsidence inversion, which prevents distribution of moisture to high levels. So that's what's happening here. The subsidence inversion, where you're getting the air to sink basically above, looks like it's about 800 millibars in the sounding, or basically between 5,000 and 10,000 feet, about 7,000 feet or so. You got air sinking from very high up in the atmosphere, above 30,000 feet, down through the middle layers of the atmosphere, and that's causing this temperature and dew point to spread, these lines to spread further apart, indicating very dry air. And that's exactly what's causing it. Now, the eastern portion and within most of the trade winds, that's where you're going to find that sinking subsidence inversion. However, weather systems or terrain may weaken or destroy the inversion, allowing empty air to locally moisten the mid and upper troposphere through convection. Convection being rising vertical air motion. Just think of a thunderstorm or a big puffy cumulus cloud. All right, so maritime tropical air masses, how do we really classify them? We're looking at what's known as the dew point temperatures. This is typically associated, empty air is associated with dew point temperatures 60 degrees Fahrenheit or greater. So if you were ever to see your evening weather report on the news and you hear the weatherman say, the dew point is 65 degrees Fahrenheit, or the dew point is a muggy 70 degrees Fahrenheit, anything 60 degrees and above indicates you're in a maritime tropical air mass. Right now, the northeast and southeast trade winds, they actually advect or move horizontally the MT, the maritime tropical air, from the subtropical highs of each hemisphere, and they bring those trade winds, bring the maritime tropical air closer to the equator into the equatorial ITCZ. Now that's ITCZ stands for Intertropical Convergence Zone. And this convergence of trade winds along that intertropical convergence zone, or ITCZ, is going to lift that maritime tropical air, and it's going to produce thunderstorms and very moist conditions throughout much of the troposphere as you get closer to the equator. You get to between 10 degrees latitude and the equator, it's going to have a lot of rising air motion, especially along this special line, the intertropical convergence zone. Now, what's the significance of ITCZ? That's the area where the trade winds converge from both the northern and southern hemisphere, and this sometimes can lead to the development of a cluster of thunderstorms and eventually the formation of a hurricane. So meteorologists tend to look at the ITCZ, and I don't know if I have a satellite picture in this presentation to show you, we'll see here in a minute, but you can definitely distinctly see it via satellite imagery, a distinct discontinuous line that kind of just straddles the lower latitudes and is associated with thunderstorms. That's the area where the trade winds are converging along. Now let's move on to another air mass type. It's known as the Maritime Polar Air mass type. It's abbreviated lowercase m capital P. Now the source regions for maritime polar air are cold, unfrozen ocean areas, generally poleward 45 degrees north or south. So I like to think in the northern hemisphere, these source regions are the North Atlantic Ocean and the North Pacific Ocean. But notice it's got to be poleward or north of 45 degrees north latitude or south of 45 degrees south latitude. The source region may be farther south, particularly off the west coast of mid-latitude continents due to northerly currents and upwelling. So when you get these ocean currents that ride down from the north along the west coast of continents in the mid-latitudes, generally that maritime polar air influence may spread a little further south due to the colder upwelling currents of the western edge of the continents. Maritime polar air is associated with portions of high or low pressure systems which reside over relatively cold water, generally poleward of the polar front. Sorry about the typo there, I got of the twice. But the maritime polar air masses form from the modification of another air mass moving over cold ocean areas. And we're going to get to that. Typically, continental polar air masses will convert over to maritime polar air masses because that with continental polar air masses, you have very cold, dry air, but once it comes over the northern unfrozen waters of the northern oceans, that continental polar air mass is going to pick up moisture from the ocean. It's going to moisten up, and it's going to result in the conversion to maritime polar air. Controlling factors of maritime polar characteristics. Now, the origin of body of air is modified to maritime polar, and as I just explained, you get a modification of continental polar air. Sometimes you can get a modification of continental Arctic air masses as well. So you get a continental polar air mass or even a continental Arctic air mass that moves over a cold, unfrozen ocean surface in the North Atlantic, for example. That CP or CA air may initially be much colder than the ocean, but that cooler ocean beneath the air mass is relatively warmer compared to the overlying air mass, and that ocean is then going to transfer heat and moisture to the cold, dry air mass, and you get a conversion from cold, dry to cold, moist, MP air. Thermal instability is common in the lower troposphere, where you get steam fog and even convective snow showers may develop. So you get extremely cold, dry air mass like continental polar air or continental Arctic air. I have been on ships over the western North Atlantic. Okay, I've been on the western Atlantic, North Atlantic in the wintertime. I've seen this firsthand. It's a real cool experience. It literally looks, that steam fog literally looks like rising smoke off the warmer water surface. You get this extremely cold air that's blowing over that warmer ocean surface, especially get in the vicinity of the Gulf Stream, and you get this weird looking fog that comes up off the water. It's a really cool effect. Modification of a continental polar or continental Arctic air mass into a maritime polar air mass may be quite rapid because of how unstable things are. You know, you get very cold over very warm, you're going to have a very rapidly rising vertical air, and that's going to allow for the redistribution of the warmth from below into the upper reaches of the troposphere, and that's going to result in vertical mixing, and that's going to cause a rapid modification of the air mass into MP, maritime polar, generally on the order of 48 hours or less. Now, a well-defined front is often present between the maritime polar air and the tropical air masses farther equatorward. And then we can also get modification, air mass modification with maritime tropical air masses. I've seen this as well. In the wintertime, living along the Gulf Coast, especially the Florida Panhandle, you'll get a maritime tropical air mass that's going to move over a colder ocean surface, or you get a maritime tropical air mass that moves over a colder land surface. And whenever you get warm, moist air to overrun a colder surface, you're going to have a warm over cold situation. That warmer, moist air is going to want to rise up and over the colder surface air, and that is going to basically result in cooling via condensation in the lower atmosphere. And I've seen this in the wintertime down on the Gulf Coast. You get some very thick fogs when maritime tropical air moves in from the Gulf of Mexico over the colder landmass. The cooling of the empty air often forces the temperature to lower to the dew point and then saturated conditions with extensive sea fog. And again, I've seen this. The sea fog rolls in right off the Gulf of Mexico, especially into the Florida Panhandle. Your visibility can go from unrestricted to less than a mile within minutes. A modification of maritime tropical to maritime polar air mass may be gradual. When you get the maritime tropical air from, let's say, the Gulf of Mexico into the North Atlantic Ocean, sometimes you get that transition from maritime tropical to maritime polar air as that warm, moist air moves over a cooler ocean surface. Just remember this, for maritime polar air, it's predominant in the air mass west of the Rocky Mountains. So when we're talking the west coast of the United States, especially the Pacific Northwest is dominated by this air mass, as well as New England states get it a lot too. Western Europe as well. The general characteristics of maritime polar air, generally cool and moist in the lower levels of the atmosphere, with very little daily temperature variation. When I say diurnal, it's just a fancy way to say daily. So you really don't get much difference between the morning low temperature and the afternoon high temperature when you're influenced by maritime polar air. And why is that? Because the air is moist, and it just simply you're not going to get a large daily temperature range with moist air. Now, another air mass that's rather interesting is known as continental tropical, and it's abbreviated lowercase c capital T. The source region for continental tropical air is generally the subtropical deserts. And guess what? Continental tropical air is only going to be around during the summer months. Okay? Or you can find continental tropical air in the tropical dry regions. The summer characteristics of continental tropical air is hot and dry conditions. If you've ever driven or taken a trip through the desert southwest, you know how hot those temperatures can get, easily above 100 degrees in the summertime. And they're very dry as well. So that is an example of a continental tropical air mass. They're often accompanied by shallow, what are known as heat low pressure systems, because the air is so intense, the land is so intensely heated by the summer sun. Summer sunning goes much higher, it's more direct, but yeah, it's very dry, so you get what's known as heat lows that form. And then continental tropical air also has an interesting atmospheric feature, atmospheric phenomenon that you sometimes will see if you're driving through the desert southwest, and that's a dust devil. And that's when you get extremely hot surface temperatures and you get the air to spin up. So continental tropical air is actually unstable in the lower levels of the atmosphere during the day when the sun is out and really baking the surface. I won't get into too in depth on super adiabatic lapse rate, but just that's really what gets things going. You get very low dew points that limit cloud development. You get a lot of bumpy motion, thermal turbulence, and then there's that dust devil formation that I was mentioning with continental tropical air masses. And they are stable during the night and usually get like a radiation inversion. When you're in such a dry area, dry air cools off 5 times quicker than moist air. So your temperatures at the surface are going to rapidly cool. If you ever go out to Las Vegas, you might be 115, 118 degrees during the day, but at night you could actually get chilly because you got such dry air, and that dry air, the long wave radiation readily escapes the space with dry air, and so you can actually get a radiation inversion where you have warmer air above cooler air at night in such locations. Now, you get low and middle clouds are very rare in this air mass because the dew points, the air is so dry, those low dew points limit the cloud development. But if you get enough heating, sometimes you can get possible late afternoon cumulus clouds, towering cumulus clouds, or even cumulonimbus, CB, forming primarily near mountains because mountains act as an elevated heating source. These type of clouds and thunderstorms they're usually high based. The base of the cloud, because the lower levels of the atmosphere are so dry, may only be 8 to 10,000 feet above the ground. You'll typically see a lot of thin, high cirrus clouds associated with the subtropical jet stream over these areas, over the subtropical deserts. Now, one thing I do want to mention is you really get those late afternoon thunderstorms and a lot of lightning, in, for example, New Mexico and Arizona. But that occurs mainly during the summer monsoon when you get some of that maritime tropical air that tends to intrude into the intense heating areas of the southwest. This is an example, a picture of the high desert thunderstorms with virga. The lower levels of the atmosphere are just so dry. What happens is thunderstorms can form, but the precip tries to come out of the base of the thunderstorm cloud. It's so dry beneath the cloud that we have virga, which is basically evaporation of that moisture before it even reaches the ground. So a lot of times you just won't get the rain to reach the ground in this case because the air is so dry beneath the cloud. Here's a good little summary of air masses across the United States and what impact us here in the U.S. You'll notice the MP, Maritime Polar Air masses, generally form over the North Atlantic and the North Pacific Oceans. The arrows represent their general trajectory of where they typically go in to the North American continent. Continental Arctic air masses, that's your very cold Arctic, record-breaking cold that we sometimes can get in winter. Definitely associated with the polar vortex, but CA is way up there, and then continental polar air masses over Canada, that's the source region, generally goes down into the central and eastern United States for a trajectory. And then you got your warmer air masses in the red bubbles. Maritime tropical air generally forms in the Gulf of Mexico and or the western Atlantic Ocean, the Caribbean. Maritime tropical also comes in the Pacific Ocean and can sometimes move into Baja as well as into Southern California. And then continental tropical air masses generally form over the heated, very dry subtropical desert areas of the desert Southwest. So that's represented there with the general direction of motion of the air mass. Now, with air masses, with the air mass modification process or changes, we can actually get different changes. When I say thermodynamic modification in air mass, I'm saying changes in the temperature and moisture content within the air mass. And this is going to definitely impact the air's density. Air masses can also be modified by topography or major physical features on the Earth's surface, particularly related to land surfaces and mountainous areas, higher elevation characteristics. Trajectory in the horizontal, that impacts air mass modification. Which path, represented by these arrows, do the air masses follow a cyclonic or an anticyclonic trajectory? That's important as far as stability goes of the air mass as it moves out of the source region. And then you have age of the air mass. The length of time an air mass has been removed from its source region is going to definitely impact how the air mass is modified. Let's take a look at thermodynamic modification first. Remember, this is temperature and moisture changes. And again, this occurs mainly because as the air mass comes in contact with the land beneath it, underlying surface as it moves out of its source region, the air mass is going to encounter different temperature and moisture properties. Now, the amount and the rate, how fast the air mass modifies, is going to be dependent upon a couple things. First, the magnitude of the air surface temperature and moisture differences. So, for example, we talked about the rapid conversion from continental polar or continental Arctic air, cold and dry, moving out over the North Atlantic, where it's relatively warmer water below it. That's going to result in rapid modification because you have a cold over warm situation, and you usually have a very large difference in temperature between the overlying air mass and the surface. And then the residence time of the air mass over the modifying surface. How long has the air mass how long has it remained over the modifying surface? Now you'll get vertical displacement or movement of the air mass. If the air mass is blown by the winds against a mountain range, that topography or changes in elevation are going to have a definite impact on air mass modification. Now, if we can add a third letter to our air mass identifier, and this is dependent on the temperature of the surface below the air mass, okay? If the air mass is aloft, above the ground, if it's colder than the underlying surface, the air is going to warm from below. And that's going to result in a colder air mass aloft over a warmer surface, a cold over warm situation. Remember the cow. That's going to result in unstable conditions. If the colder air mass is moving over a warmer surface, that is going to be suffixed with the letter K. That'll be the third letter in the identifier. On the other hand, if the air is warmer than the underlying surface, so now we have warmer air moving over a cooler surface, air is cooled from below, this is going to promote stability, stable atmosphere, warm over cold, this is going to be suffixed with the letter W. Moisture added by evaporation, liquid converted to a water vapor, or sublimation, which is frozen from, oceans can definitely modify air masses, the moisture content. They are most important in the oceans. Such a large body of water. Lakes and rivers can also modify air masses and change the moisture properties. A moist ground. And then ice and snow, they don't do a whole lot. Ice and snow are going to act like a landmass, really. There's just not much in the way of moisture that's being added into the atmosphere. Removal of moisture by condensation, that would be a conversion from a vapor to a liquid. Deposition, solid, vapor to a solid, and precipitation may affect stability. So for example, if you have moist air mixing with dry air, okay, if you have the same temperature, the temperature stays the same, but you have a drop in the water vapor content, you're going to increase your air mass stability. All right, and without cooling from an external source, such as a cold surface or radiational cooling, removal of water vapor through condensation or deposition will decrease stability through latent heating of the air. We won't get too in-depth on this. We're just going to keep moving along. I don't want to get too technical on the video, but there are some changes via these processes, moisture by condensation, deposition, precipitation, all that type of thing. Now, topography mountains are very important. The amount of air mass changes or modification influenced by mountains really is dependent on the orientation of the mountain range with respect to the wind direction, that prevailing predominant wind direction, and how high the mountain extends in elevation. Okay. Now, in the United States, we happen to have a lot of north-south oriented mountain ranges. We have the Rocky Mountains, we have the Appalachian Mountains, Pacific Northwest has the Cascade Mountains, and our general weather in the mid-latitudes moves, our general winds blow from west to east. So a lot of cases, you get a perpendicular wind component to these north-south oriented mountain ranges, and that is going to have a major impact on air mass modification. Because air masses, as they are lifted over large mountain ranges, they experience extreme modification. On the windward side of the mountain, that's where you're going to get all your precipitation. All that moisture is going to be taken out of the atmosphere. As the wind blows up against the mountain slope, that's going to all be wrung out like a sponge. Have you ever wet a sponge before and you just wring out the moisture from the sponge? That's exactly what happens when this air mass is blown by the west to east winds in the mid-latitudes against the north-south mountain range. That air is going to rise up the windward side of the mountain. As the air rises, it cools, it condenses, and precipitation falls out of the clouds. So a lot of decrease in stability due to that mountain lifting, that orographic lift on the windward side. But then on the leeward side, the air begins sinking, it goes down the mountain slope, air is adiabatically warmed and dried out. As air sinks, it dries and warms, and that's going to result in a much better stability, increasing stability due to sinking air motion or subsidence in the atmosphere. So air masses which move parallel to mountain ranges, those on the other hand experience very little change. This happens over as the air comes down off the Siberian continent, the Asian continent. You got the east-west oriented mountains, and I'll show you that. I think I have a picture of that. All right. Now, what about air mass modification with unfrozen lakes or water bodies? This is very important for those that live in the lake effect snow belts, especially in fall, late fall, and early winter when those Great Lakes are not frozen yet. Greatest effects are generally observed on the lee side of the lakes. You have continental Arctic or continental polar air masses starting to come down from the northern latitudes. They cross large, relatively warm lakes. And again, it's generally a late fall and early winter. The Great Lakes just aren't frozen yet. So you get this extremely cold, dry continental Arctic or continental polar air moving over the Great Lakes, over the unfrozen Great Lakes, picking up heat and moisture from below. This results in intense warming and moistening. And you get steam fog, and you also get intense vertical mixing that may result. You get significant RW, rain showers, SW, snow showers. They may result from the 5,000 to 6,000 foot tall convective clouds. It doesn't take much vertical lift to really get a lot of moisture to fall out of the clouds on the leeward side of these Great Lakes. Here's a great diagram to show this. Continental polar air moving in from a very cold landmass at 0 degrees Fahrenheit. And that blue arrow represents the flow of the continental polar air. It's dry and cold. It's moving over that water at 32 degrees Fahrenheit. So there's a large temperature difference, very cold air over that water. And what that promotes is rising air motion, the little green arrows there. That rising air motion, that rising air eventually cools and condenses, forming these gray, you see these clouds are represented by the gray. the gray symbols there. And snow falls over the lake and generally downwind shore. But the downwind shore gets hit hard. Places like Buffalo, New York, places like Erie, Pennsylvania, they get hit hard because of this continental polar air. The UP of Michigan, you look at the Michigan lake effect snow belts, you look at even Indiana sometimes gets hit hard, depending on the wind direction and the trajectory of the wind. How long does that wind blow over? What's the total distance that wind blows over that warm, unfrozen body of water, those lakes? Here is a great example of, what are the results of the lake effect snows. This caused some very high annual snow amounts in Syracuse, New York, in Buffalo, Cleveland, Ohio. Can't leave Cleveland out. Downwind of the unfrozen Great Lakes is where this typically happens. The top image shows the light blue colors associated with radar reflectivity. Shows snow falling the lee of Lake Michigan, Lake Superior up in the UP of Michigan. Also, Lake Ontario, or Lake Erie, Ontario, yes. Even in Erie, Pennsylvania, these areas get hammered. The bottom left image shows the satellite image of these lake effect, what they call streamers. And then the bottom right shows two gentlemen out there talking, how are we going to dig out of this? How am I going to get this vehicle that's behind us shoveled out so I can actually go somewhere? I mean, that's a kind of, we're talking feet of snow. Feet of snow. As long as the wind trajectory is there, as long as the wind keeps blowing, it keeps picking up moisture from that warmer, unfrozen body of water and just dumps snow. Finally, the trajectory of the air parcels, or the air mass. This is going to be important as determining stability of the air mass. The trajectory of air parcels is influenced by the type of surface and the topography, the elevation encountered, thus affecting air mass modification. However, here we go. The curvature of that trajectory may also influence the vertical motion and potential stability of the air mass. First example I'm showing is that black L, letter L. That represents an area of low pressure. The red arrow shows the trajectory. You got cold, most likely continental Arctic air coming off Siberia. You got a cyclonic trajectory here, in this case. With a cyclonic trajectory, what that does is it increases your convergence or rising air motion in the lower boundary levels of the atmosphere. And you get mass convergence, which increases air mass thickness. The air mass is deepening. A lot of rising air motion increases the air mass thickness. The atmosphere wants to expand in this case. The air mass deepens, and that mass convergence enforces rising air or ascent at the top of the boundary layer, which will decrease the air mass stability. So with a cyclonic trajectory to an air mass, it's unstable conditions. Indicates air mass involvement with a synoptic scale cyclone, possibly jet stream lifting mechanisms. So not only do we have the low pressure system here that's promoting rising air motion, a lot of cases you have a jet stream in this part of the world that, areas of accelerated wind speeds known as jet maxes, and I've talked about that in previous training, can actually promote rising air motion and the removal of mass aloft, the chimney effect, upper level divergence. And in this case, if you were to look at air mass classification, you see a suffix of U on the end. That means it's unstable. U stands for unstable. You know it's a cyclonic trajectory of the air mass. On the other hand, you have an anticyclonic trajectory. The black arrow and then the red arrow represent that anticyclonic or clockwise flow around those high pressure systems that are situated over the subtropical area there of the Atlantic Ocean. So this is an anticyclonic trajectory with a maritime tropical air mass, most likely. So anticyclonic trajectories, these actually increase frictional divergence. Mass divergence will decrease the air mass thickness. The air mass becomes shallower. Mass divergence then forces descent. Sinking air motion at the top of the boundary layer. Sinking air results in more stable atmosphere. Excuse me. This indicates air mass involvement with a synoptic scale anticyclone or high pressure system, and also you can be in the jet max area where the air is actually sinking. Now the air mass is suffixed with an S in this case, the letter S, stable. And then air mass age. Another thing to contemplate when we talk about modification, the longer the air mass is away from its source region where it formed, the more modification is possible. Selected examples of air mass characteristics as they traverse the U.S. during the winter and summer. Just a couple examples for you here. We're about to wrap things up shortly, I believe. But generally, in winter, maritime tropical air over the Caribbean or the Gulf of Mexico generally originally displaced temperatures in the 80s and dew points in the 70s. Upon traversing the cool coastal waters and colder land over the southeast U.S., the air mass has experienced some cooling and loses some moisture via condensation, producing dew and advection fog. So air masses change over time. Right? This is an example of an anticyclonic trajectory, stable, usually get a warmer over a cooler situation, which results in saturation of the lower atmosphere and the formation of dew and fog. Okay. Here are some examples of, I'll just quickly go through these winter characteristics of air masses. For continental Arctic and continental polar air masses are dry and cold and stable over land. Usually get clear skies at night. You may have scattered flat and stratocumulus clouds during the day. Under brisk northerly winds on the east side of the anticyclone, visibility is usually excellent. Okay, and then you get excellent radiational cooling and calm winds in the center of these high pressure systems associated with polar highs, continental polar and continental Arctic air. Generally produces some very cold temperatures, freezes or heavy frost at night. And then there's only a limited modification of air mass, especially if you have a snowpack. In extreme conditions, continental Arctic air has produced temperatures less than zero, below 0 Fahrenheit as far south as the Gulf Coast. All right, that I think I'm gonna wrap things up tonight. There are a few more slides here, but I think it's a good point to wrap it up. This just generally shows you the differences in air masses and how they change. Just keep in mind that air masses do go through some modification as they leave the source region. One thing I didn't mention was this cold air damming condition, which occurs in the eastern United States, generally east of the Appalachian Mountains. And this produces a lot of fog, drizzle, and low stratus clouds, that dull gray, very gloomy winter day you can sometimes get. So that's a very important concept when you have this cold air damming. That cold air just gets dammed or pushed up against the east side of the Appalachian Mountains. And that can have a major impact on precipitation type, especially in the wintertime. Maritime polar air masses are cool and moist in the low levels. Very little change of temperature between day and night, or morning and afternoon, I should say. And maritime polar air masses are generally milder in both winter and summer. They're chilly. They are chilly. You'll need a coat, but it's not like the continental polar air masses where you're freezing. Just that cool, damp air. That's the best way to describe maritime polar air masses. And sometimes you get these widespread stratiform precipitation when forced to ascend along the front or in a cyclone. All right, that wraps things up. That wraps things up on the air masses. I'm going to go ahead and wrap it up after that. We've been going quite a while here on the training tonight. I hope you've enjoyed this presentation. Keep in mind that I am working on a winter weather forecast, what my winter outlook is going to look like for the 2019-2020 winter. We just had Hurricane Dorian go up the East Coast here in early September 2019. So there may be some changes to the forecast as far as nor'easter development. But stay tuned for that. And I'm looking forward to doing some more weather videos as we get closer to the wintertime when things become more dynamically active. That wraps things up. A Spot on Weather. Hope you enjoyed this training on air masses. Air masses are such an important part of storm development, especially in the middle latitudes. All right. Take care, everybody. I hope you enjoyed this training on air masses. Take care, everybody. Have a great evening. Stay safe. Until next time.